In this video, we're going to take a brief look at the conservation of momentum. Okay. Now, this idea of conservation of momentum relies on the idea of a closed system. So we have a closed system, and in this particular case, in this example before you, we have two masses, M1 and M2. They are in motion, in this case towards each other, but they represent a closed system. There are no other forces or objects interacting upon them. So they constitute their own closed system. Now within that system, the momentum of objects is conserved. So the total momentum of this whole system, if you look at the mass times velocity of each of the masses, if you sum that and got a value, and then looked at that after those two particles had interacted with each other in some way, again, you're still going to find the same conservation of mass. Okay, so there's no extra outside forces acting on this system, and so the total momentum will always remain constant, including when these objects interact with each other. So even before they interact with each other, you're still going to have constant total momentum. Okay, let's say they're on a collision course with each other. Again, there's no outside forces acting, then they will collide with each other. But still, the total momentum of the system will be conserved before they collide, after they collide. Okay, it's a quantity that remains fixed and does not change. Okay, even when they interact with each other, so long as there's no outside forces or objects acting upon them, as long as they remain a closed system, the total momentum will remain constant. Okay. So the principle of conservation of momentum states that the initial momentum is equal to the final momentum. And when we say that, if we look at the total momentum on the left here before they collide, we sum that up, we'll find that's the same after they've collided and moved off in their opposite direction. The total momentum of the system remains fixed. We can look at the velocities of the objects as u1 and u2 before collision, and then we can look at their velocities after collision and call that v1 and v2. Okay, the masses of course don't change, and we will find that the mass of object 1 times its velocity plus the mass of object 2 times its initial velocity added together will be the same as after the collision, the mass of object 1 times its velocity v1 plus the mass m2 times its velocity v2. Okay, and to see this in action, there are numerous examples we could pick. I've only picked one here for us, but a shell of mass 5 kilograms is fired from a gun of mass 10 ton mounted on wheels. Okay, we're going to assume frictionless forces. The 10 ton gun is able to move without friction on the wheels there, so there's nothing interfering with it. So we have our closed system. We have the gun and the shell sitting together. Okay, the shell is sitting in the barrel of the gun, no problems. Okay, afterwards they've separated and moving off in different directions. Okay, but the total momentum before, when they're both sitting together and both at rest, will be equal to the total momentum after. And to see that, we note that the gun recoils with a speed of minus 0.1 meters per second. We want to find the speed of the shell. Okay, so again, choose a direction. So we're going to choose to the right as positive motion. There's no upward motion in this case, but anyway, we're assuming everything occurs horizontally. Okay, motion to the right is positive, motion to the left is negative. So it must always have a direction. System, our coordinates must always recognize that. So let's find the speed of the shell. Well, we need to have a look at the situation before first. Okay, we have the mass m1 times u1 plus m2 times u2. Well, for the mass m1, we've got, what was it, 10 ton, wasn't it? Yep, 10 tons, so it's 10,000 kilograms times it's at rest, so the initial velocity is 0. The shell is 5 kilograms, it's at rest too, sitting in the barrel of the gun, nothing's moving. So on the left-hand side here, what we have is total momentum is 0. Let's have a look at the momentum afterwards, after they fired. So we have 10,000 kilograms times negative 0.1. It has to be negative 0.1 because it's moving off to the left. Okay, the shell on the other hand is going to move off to the right, so it's 5 kilograms times some unknown velocity. 10,000 times negative 0.1 will be minus 1,000 plus 5 times the velocity of the shell, whatever that is. We can find that by solving. Let's take 1,000 onto the other side. We have 5 times v is 1,000. And then dividing through by 5, we have a velocity of 200 meters per second in the positive direction. So the total momentum after the interaction sums to 0, because minus 1,000 plus 5 times 200 is 1,000. That sums to 0. So total momentum after the shell is fired is 0. Total momentum before is 0. Okay, just remember that is the total momentum. All the parts of the system, if there are more parts than the 2 given in this example, all of it must be taken into account. And it must be a closed system. There's no outside interactions. Okay, that's it.